Hello, we are Team 25024 doing fourth generation electrical ground support equipment, or EGSE, for Northrop Grumman Chandler. Our team members, sponsors, and mentors are listed here. EGSE is used to provide external power to avionics equipment and squibs on NGC launch sites and vehicles. The current design has issues with ramping up production due to procurement difficulties and high labor times stemming from an outdated design. Design principles we are using will help save NGC over $1.5 million over the course of 5 years. What we are designing is a custom circuit card assembly, or CCA, that consists of a 16-channel power switching motherboard and a microcontroller-based daughter board. Supporting the hardware is custom firmware and software developed by our team, and the mechanical design consists of three identical units all housed within a standard 1U rack mount space. Shown here is the launch layout, where you can see that our unit housed within the VIC, or Vehicle Interface Control Rack, sends power to the launch vehicle and communicates status via Ethernet. Next, we will cover the design and verification section of this project. Originally, we were given the schematics and PCB files for the motherboard design and tasked with improving it in a couple of ways. Some of the changes include implementing a new relay switching system, updating the daughter board connection interface, implementing 8-bit shift registers for individual channel control and status monitoring, as well as redesigning the routing and layout of the PCB itself to fit within a 19 by 5-inch space. On top of this, the component selection for the over 50 unique components was optimized to prevent obsolescence and supply chain issues in the future. The verification procedure for the motherboard itself boils down to providing power to the boards and channels through the adapter module shown below and the custom wiring, and ensuring that the 65 volt at 10 amp maximum requirement is met for each channel.
Section 2.2, Daughter Board Design and Verification. We were given requirements by our sponsor to design a daughter board all the way from its schematic creation and designing those components using OrCAD Professional, all the way to its PCB fabrication, as you can see in the image below. Some of the main requirements was having a 2 by 1 inch size requirement so the board can sit nicely on the motherboard. We had to include a microcontroller interface and headers that will hold for MCIO pin configuration support, LED, and SPI communication support toward the motherboard from the MCU on the daughter board. Next is the Ethernet PHY and the RJ45 connector for connection to the outside world. The next steps is to solder, assemble, and test the daughter board unit. For verification, there are 4 modules we will be verifying: power supply validation, microcontroller execution check, Ethernet connection with the RJ45, and GPIO functionality.
So here's a software overview. Our implementation controls a 16-channel power switching PCB with microcontroller-based remote operation. The firmware uses Microchip's MPLAB IDE, XC32 compiler, and Harmony framework on the PIC32MZ starter kit that's shown right here. Our Python GUI is containerized with Docker for consistent deployment, while CI/CD pipelines and SonarQube ensure code quality throughout development. On our next slide, we've implemented a clean layered architecture. The user interface layer provides our Python GUI. The application logic layer contains core functionality. The middleware layer offers reusable services. The hardware abstraction layer bridges software and hardware, and the hardware layer interfaces directly with physical components. Here is our firmware capabilities in a modular block diagram. The key capabilities include a built-in test on power-up, memory sanitization, field upgradable over Ethernet with checksum verification, default IP configuration via front panel, tricolor status LED for unit identification, configurable startup states, channel lockout functionality, and robust SPI I2C interfacing with simple UDP communication.
This is a Python-based GUI for our 4th gen EGSE. Each row maps to a power switching channel showing live voltage and current via UDP from the PIC32 firmware. Operators get one-click control over FETs, relays, voltage sense, and ADC. The utility tab shows relevant information plus any user actions or errors for full traceability. To make handoffs seamless, we package the GUI in Docker. It includes the Python runtime libraries and tests. It can launch with a single Docker run on any OS. SonarQube scans for bugs, vulnerabilities, and code smells. We're passing with A grades, proving the code is secure, clean, and compliant with our sponsor software assurance standards. GitLab is where we store our code for continuous integration and continuous deployment. Our pipeline triggers automatically with every GitLab push, running 15 unit tests to ensure functionality works as intended.
Each mechanical unit of the 4th generation EGSE product is comprised of 3 subunits, also known as subchassis, which are housed in a total of 1 U shelving space. Each subchassis houses an electrical assembly and the interfaces required for EGSE components to communicate with outside hardware. The focus of the mechanical redesign was for modularity of components, ease of access for NG technicians, and machinability to reduce production time. Moreover, it was designed for longevity and resistance to expected environmental stresses on the launchpad, such as coastal salt fog and high mechanical vibrations. Aluminum 6061 was chosen as the overall fabrication material for the subchassis. It was compared with stainless steel and aluminum 7075 for corrosion resistance, cost, durability, and machinability, most importantly. Although stainless steel and 7075 have high corrosion resistance and durability, they are also high cost items which are more difficult to machine. Thus, 6061 was chosen. The subchassis was manufactured using conventional subtractive manufacturing techniques such as manual and CNC machining. Individual mounting components, as seen here in the front port cap assembly, were used to simplify machining processes by running components in parallel during fabrication, which reduced the overall time. Moreover, the designs were focused around standardized stock and screws, reducing the assembly complexity and the overall risk of the mechanical design.
So moving on to the subchassis, you can see the subchassis here in the 2 photos, the front port cap on the left and the rear port on the right, as well as I like to point out the insulation pads, those black strips running along the bottom of the U channel that are used for electrical insulation. Here are our system requirements for verification. Notice that 2 of our requirements, 2.1 and 2.4, were deemed out of scope and out of budget for this iteration of the project. So we recommend the next iteration complete these steps during their project. And finally, the 3D model and rendering exploded view here. You can see the top plate above and then the U channel below, as well as the front port cap and rear port cap on either side, as well as the modular aspect of them, as well as the plugins for each side of the port caps.
Here are our deliverables and lessons learned from this project. What we will be handing off to Northrop at the end of the semester is a functioning EGSE unit with one of the 3 modules fully populated with all components and wiring. Going along with this unit is a design file package containing CAD, schematic, PCB, firmware, and software files. A final report containing detailed design narratives, assembly processes, and testing methods on top of a comprehensive acceptance test procedure will also be provided. We learned many lessons that will be vital going forward into our careers. First is the need to ensure the entire team is on board with the design decisions to avoid confusions, which ended up causing setbacks later in the project. Second is the benefit of reaching out directly to manufacturers and fabricators during the design process to ensure no issues crop up when fabricating and assembly actually occur. Finally is the importance of proper and accurate documentation. Thank you for your time, and we look forward to seeing you on Design Day.